the recording and sharing my screen. And then, so as a reminder, today, midnight, your the Twitter Postgres indexes assignment is due. Again, lots of computation in this assignment and very few submissions so far. So I expect there will be people who not able to get it complete in time just for purely computational reasons. And if that is the case for you, my recommendation is that you will probably get significantly more points turning in a correct assignment late than an incorrect assignment on time. The late penalty for the class, 20% per day. So that will probably be less than the points that you would miss from turning it in on time. Before we get started for today's material though, any questions about the homework assignment or anything administrative or anything at all? Okay, then in today's class, we're going to talk about the last topic for our class. We have, I mentioned under this week 13 folder, there's this folder search engine, which has your last assignment. We'll be going over that last assignment today. And this assignment is, well, the purpose of it is we're going to be building sort of a web search engine. We saw very beginning of the semester how that, the end product of what that might look like. Now we're in a position to fully understand all the components of that, and you get to build it yourself. This will also introduce us to our common crawl data sets, the data sets of the internet that are petabytes in size, and how to work with those. The material for this assignment is not going to be directly on the final exam. There won't be any questions about anything specific in here to the final exam. It will be focused on the previous stuff. So the purpose of this assignment is really just to do this assignment. So the first thing for us to go over is to remind ourselves, or to see this little picture again, and it's very faint here in the, hopefully that makes it a little bit better. Zooming in, very faint on the screen in the room here. But this is the picture that we saw maybe from week 2 in the class of that Instagram tech stack. And we had some sort of web app which had 4 different layers to it: the load balancer up top, the Nginx, then the web server, which we're using Flask because it's super simple. Instagram happens to use Django. Then a load balancer, a PG bouncer, and then the database at the bottom layer storing the actual information. And now that we've fully sort of understand most of the important stuff about Postgres, we're able to talk more about using this this tech stack for applications. And so the new thing here is that we'll have these sort of auxiliary tasks, like a web scraper, or drawn just 2 random auxiliary tasks down here that talk only to the Postgres database and not interacting with clients coming to the website, to the web server. And this is how we can load data into the database. All of the data loading that we've done before with the Twitter Postgres assignment, that was done not inside of a Docker container, so it was done on the Lambda server, so not super scalable, not arbitrarily scalable to an arbitrary number of machines. In this assignment, the web scraper tasks, the tasks that are actually going to be accessing the data from this common crawl archive and putting them into the Postgres database, they will be inside a Docker container, so they could theoretically be running on different machines, arbitrary number of machines, and you could get essentially infinite scale up just depending on how much you wanted your credit card to be bill to be on AWS. This is sort of the key picture about how information is going to be flowing that you should keep in mind as we go over the search engine assignments. Any questions about that? Okay. So in the search engine assignment, again, due date week from today, and don't want to have the collaboration extension because your final is going to be given to you on Friday after this, and I want you to be able to focus on the final and not have to worry about this or other assignments for the class. There's going to be another sort of computationally intensive assignment, and so another one that I recommend not putting off until Wednesday or Tuesday night, because then you probably will not have just time available to complete it. But the sort of key takeaways from this assignment, so there's going to be like a pretty large software project. There's maybe like somewhere between 10 and 50,000 lines of code in here that you're going to have to navigate to do different things with. Again, we're parallelizing all of our data analysis so that it's arbitrarily scalable. We're going to see these things called WARC files used to store pretty massive web crawl data sets, so multi-petabyte data sets. And we'll be using a lot more indexes. And then really one of the key things here is that this system, as it's currently written, has a bug in its database performance that when you access the web page, once you when you access the web page, do a search query, whatever you're searching for, the results down here are being returned with a sequential scan. So the runtime will be linear in the size of the data set, and you'll have to figure out how to fix that, figure out where the query is that's causing that bad performance, and write a good index that will fix it. So the project setup, pretty similar to all the previous projects of forking this repo, cloning the fork on the Lambda server. I think there might be already 1 or 2 students who have done this already. There's been, just this morning, I was making some sort of last minute adjustments to the instructions here. So I'd recommend re-going through these steps if you've already done it. And then you'll want to not start this assignment until after you've finished your indexing Twitter assignment, because you're going to need all the disk space on your big data partition in order to do this assignment. So you delete your previous big data folders following the instructions in the last assignment, and then also, again, making sure that you have pruned off any volumes that are currently in use so that you have enough disk space. In terms of getting the system up and running, there's a lot of Docker-specific stuff that's going to go on here, or sort of application-level specific stuff that we haven't seen in a while since the beginning of the semester. So I would expect this task to maybe take a little bit longer than the getting the system up and running tasks for the Twitter assignment. Again, there's multiple Docker Compose files. We saw how those worked long time ago. And a new thing here is this create passwords.sh script. That this script is going to, we talked about before, there's this .env.prod file, which I'll go ahead and, normally I wouldn't ever show production passwords, but since this is just the homework assignment, not a real production password, here is the password to the database. And in order to make secure passwords sort of automatically, there's a script, the script create passwords.sh, and this file just generates this .env.prod for you. A good reason to have a script generating these sort of passwords is so that you can use continuous integration like GitHub Actions to test your system end to end on small amounts of data. So that's part of the setup, getting this file. You don't create it manually, the script creates it for you. You'll have to modify all of the ports like we've had to do in the past. And then building the actual Docker containers. This is, so these Docker containers contain a number of extensions to Postgres inside of them, one of them being the rum extension. And it has to build, compile all of those things. And so this line right here, I would expect it to take maybe an hour or so to run. So again, computationally intensive, don't put it off until the last minute. When you're connecting to the database, the username that you'll use is Novichenko. That's the username that's created in this production inf.prod file. The reason why I chose this username, it's a particularly famous person in North Korea because he was a Soviet military officer who the US was trying to assassinate Kim Il-sung before the Korean War, had somebody throw a grenade at him at a speech, and this guy grabbed the grenade in the air and threw it back. And as a former military person, that is just an exceptional story. This search engine is also something that is deployed inside of North Korea to help them search documents, since they're not, for various reasons, not able to use Google. Enable SSH port forwarding. Talked about how to do that before, and then verify that you're connecting to that to the web server using Firefox. And then one last check this, check Web Endpoints. This is sort of just a end-to-end script, runs a bunch of things to make sure that everything is working. You have a sane environment. And when you run this, you should get a bunch of things saying pass. And so it'll look something like, oops, need the SH in front of it, something like that. Just 3 test cases in this case, and they should all say pass. If all that happens, then you have successfully brought up the project, and you haven't, at this point, no changing any code or anything, but good chance of things being slightly out of order or weird things going on, and this task 1 taking a while to complete. Any questions about that first task? Question is, can you send this to the background? It would be perfectly fine to no-hup this, put the ampersand at the end, and let it run in the background. Yep, that'd be, in fact, an excellent thing to do. Good question. Any other questions? Okay, so at this point, if you were to connect to your web server, you would just see something like this. And if you typed in some search term, you would just get some, in this case, I've already loaded a little bit of data so we can have something to look at, but you would just get an empty graph up here and empty search results down here. There's two Docker services for loading data into the web page. This one, downloader work and downloader host. The downloader work is one that I fully provide to you. You don't have to make any modifications to, and so you can do this task A without doing any coding at all. It's again just following step-by-step instructions. The downloader host you complete after doing the task 2A, and you'll have to do a little bit of modification to Python code in order for this one to work. For talking about the loading the data steps, though, let's go back over to the notes and talk about the data sets at a little bit more high level. And so the first thing for us to talk about is scaling here in Postgres in this database. So there's two common types of scaling that people will talk about: vertical scaling and horizontal scaling. Vertical scaling is like what the Lambda server is. It's just a really powerful single machine, lots of RAM, disk, CPU. And vast majority of situations, vertical scaling is what you want to do. Horizontal scaling is adding more machines instead of making those machines more powerful. Trade-offs for vertical scaling is that it's actually super cheap these days to do vertical scaling. So like the Lambda server, 256 gigabytes of RAM, 80 CPUs, purchased 3 years ago. That machine cost about $10,000 for those components. So I mean, it's not nothing, but compared to like engineering salary or engineering time to do horizontal scaling, or to compare to like AWS hosting bills, it's effectively nothing. The only downside of the vertical scaling is that there is an upper limit, like a maximum amount of hard drives you can physically shove into one machine. And so horizontal scaling lets you overcome that. It requires about typically 10 times the amount of resources as vertical scaling for the same performance. Doing horizontal scaling, getting the same performance as the Lambda server, I'd expect to spend about $100,000. But there is no upper limit, so I could go up to $1 million and get 100 times performance. Yeah, vast majority of, let's see, outside of FANG companies, I've seen a lot of companies go this horizontal scaling route, and not one of them, it was actually worthwhile. They would have saved a lot of money and time and resources doing the vertical scaling route. So almost certainly that's what you would want to do in the future at your own companies. So another couple acronyms that you'll see a lot with Postgres and with other systems are OLAP, online analytics processing, really only for read-only workloads. Think of OLAP as a synonym for basically read-only. And these are pretty easy to scale horizontally. So things like search engines, any sort of data analytics or data science applications pretty much all fit into this category. And it's easy to scale horizontally. You just replicate your database however many times you need, changing what the appropriate settings in your Docker Compose file, and everything now you can just magically support 10 times more users. So this is not too bad. OLTP, online transactions processing, this is more like what Instagram is doing, where you have people actually interacting, manipulating things, updates, lots of inserts, not just selects. This is a lot more difficult to scale horizontally. And the key idea is, how do you ensure that the writes get propagated between machines? So like up here in this sort of scenario where you had multiple Postgres databases, if you write to one database, how do you make sure those writes go everywhere? Turns out to be a pretty hard CS problem. We're not going to talk about that problem, though, in this class. It's just good to know that if you see people talking about OLTP, they're really focusing on like the writes and the updates. See people talking about OLAP, they're talking about the selects. Okay, so into the data set. Web scraping, where do we get our data from? There's going to be 3 data sources that we'll look at. The first one is the Internet Archive, so archive.org. Pretty big data set, 50 petabytes as of 2014, so as of a really long time ago. That's the last published information that I could find. And this is really the best source of data for what the web looked like in the past. A number that I find particularly amazing is that the Internet Archive is gobbling up 40 gigabytes per second on the internet continuously over the past decades. This is actually getting into the realm of what I would call big data, the things that are just like a file that is a gigabyte in size. That's not really big data compared to gigabytes per second. That's huge. So petabytes per month of data transfer. This is all open source code. If you wanted to look at it, there it is. And yeah, I might consider Wikipedia the real foundation or archive of human knowledge, but just because it's easily accessible, archive.org though, definitely a lot more stuff in there. The other data sets, Common Crawl. This one's more commonly used by researchers for, it's a little bit more accessible, but it's still quite large, over a petabyte. It goes back to 2008 instead of back into the 90s. This, yeah, again, standard archive for scientific research about what the web looks like now as opposed to the history of the web. Internet Archive is hosted on custom hardware, custom data centers. Common Crawl hosted on Amazon S3. So it's one of their cloud providings. S3 is good for storing large distributed static files. Very high uptime with no data loss. I don't know of any incidents where S3 has had data loss. But the downside is that it is super expensive. So Common Crawl, again, on the order of petabytes. They're spending $21,000 per petabyte per month on their hosting here. Oops, did not mean to click on that image. And then data transfer fees. Anytime somebody downloads the entire Common Crawl from the web page, it costs $50,000 per petabyte to the Common Crawl project. So this is quite a bit of money right here. S3 is not cheap. In general, cloud providers are not cheap. But fortunately for the internet community, this hosting Common Crawl is Amazon does for free. They donate all these resources. So there's no nonprofit or anything paying for it. It's just Amazon is paying all of this money. There's literally hundreds, thousands of examples of people doing really cool stuff with Common Crawl. So I would recommend just clicking that link and browsing through it. Some of the cool things that two examples I thought were cool. So mapping the discussion of congressional bills, like which news sources talk about which congressional bills. Or so RSS is a dying, pretty much dead internet technology. You can map how it rose and then died off on the internet. Last option. So yes.
What about paywall news sources? Are they able to circumvent that, or is it not available?
Great question. Question is, what about paywalled news sources? So New York Times, Wall Street Journal, all these websites have paywalls in front of them. It's a complicated issue. So Google, all of these websites allow Google to access their web pages because they want people to be able to find their web pages through Google. So the paywall really only exists for humans and people who are able to convince these websites that they are Google get allowed access. Wall Street Journal is notorious for being really, really picky about allowing other people to have crawling access to their news articles. Basically every other news source that you've heard of is going to be inside of Common Crawl and Internet Archive. And even Wall Street Journal, most of those, 90% of them are going to be in Internet Archive. Related to that though, one of the something very controversial about web scraping, which I don't think I have a link in here, but as of a year ago, congressional websites, so senate.gov, did not allow anybody except Google to scrape information off of their websites. And so that information not available in Common Crawl, not in the Internet Archive. And very controversial for a government taxpayer-run organization to sort of be favoring a particular private entity that way. I believe they have changed their policy since then. But yeah, so there are some limitations to these data sets, but limitations are much less than you would think they are. Does that answer your question? Yeah. And so last sort of way of getting data, writing a scraper manually. So first of all, this is really not recommended unless you really, really need fine-grained control of which pages you get access to. So for example, if you needed like things that required a login, like actually going inside of Facebook and scraping things that way. But this is really hard to do. And as a demonstration of just how hard it is to do, here is Larry Page, so founder of Google, publishing on an email list, complaining about how hard it was to write his web scraper back when Google didn't exist, and he and Sergey Brin were trying to create it. There's this sort of famous meme, not in the sense of like the pictures, but in the sense of like just in people's heads of people in the know, that Joseph Miller right here, because he helped Larry Page actually answer his question on how he could create his web scraping engine. He's really like a co-founder of Google, but he has not been compensated for this question right here, which probably resulted in billions of dollars of economic gain. So poor Joseph. One of the reasons why it's really hard to write these web servers is there's this thing, robots.txt, which describes like how a well-behaved scraper should interact with a website. And obeying robots.txt is, in general, like hard in the most difficult cases. So even like major companies like Facebook make major mistakes. So here's an example of Facebook basically shutting down, DOSing a couple of websites because some new engineer at Facebook made a mistake in their web crawler, and Facebook was making too many requests, bringing down web pages. There's a lot of talk about, I don't know, or questions people have if it's legal to scrape data. And the answer is that in the US, a number of court cases have ruled that it is 100% legal for you to scrape anything that you can get. If a web page is willing to give it to you, you can take it and do whatever you want with it. And so if you are the owner of a web page and you don't want people scraping your web page, then you have no legal recourse to that. You must use technical measures of detecting that somebody is using a bot and blocking them through those technical measures. Can't sue them to get them to stop. So this is usually the like sort of first choice of people who are doing, I don't know, web analytics for the first time, but this is the worst choice, not what your first choice should be. Really the common crawl, it's, as we'll see, it's pretty easy to use. This should be your first choice on how to get large sort of snapshots of sections of the internet. No matter which one of those three choices you use though, you're gonna be storing results in what's called a WARC file, stands for Web Archive. This is the standard format for storing a web crawl history. And so if you remember, there's this downloader WARC. Basically what you're gonna do, or what this program right here does, is it takes a WARC file as input and just adds it into the search engine. So these WARC files, again, invented by the Internet Archive in the 90s, evolved from an older thing called an ARC file, not in use anymore. WARC files also now the official file format for the Library of Congress. So lots of reasons why this is the standard thing to use. And so if you are building your own scraper for whatever reason, you definitely should use the WARC file formats. And the reason why it's good is that it provides a complete history of the HTTP sessions and not just like the the information that like the web pages themselves. And it turns out there's a lot of information in the session that you actually need. So for example, the main is the encoding of a web page. It is possible inside of HTML to specify that a web page uses a certain type of encoding, like UTF-8 or UTF-16. And you need to know this in order to interpret like what the characters in the web page mean, how to handle foreign characters, or you basically can't load a web page, understand the HTML without knowing this encoding information. But this is not always specified in the HTML. It can be specified in the HTTP header. And so if you don't have that information from the work file, then you're not going to be able to decode your text properly. And when you look at it, you'll get lots of these weird like question marky things from not doing Unicode correctly. So there's another sort of, again, common mistake of people who are doing their own web scraping, not using this work file, is you don't get the encoding correct on the web page. And so you get lots of weird artifacts in your HTML. And it's super hard to debug. But by using the common crawl, you avoid all those problems. All of that's taken care of for you. And you'll be able to get the HTML out and actually work with it pretty easily. Super fast overview of that. Any questions about it? Okay. Then the next part, we'll talk about in detail how to actually use the Common Crawl website in order to get access to these work files. And so this is the thing that you'll actually like need to be able to follow along with in order to complete the assignments. So in this task 2A, there's this link right here. This link takes you to this location right here, so you're ready to get started. And here, there's a bunch of links to all of the different, this is the entire like Common Crawl archive, links to all these petabytes and petabytes of data. And on any one of these, or they've broken up all of their data into roughly month-ish long chunks. And if you click one of these, then there's a bunch of different types of data stored here. The thing that we want are the work files. The other types of files are all like metadata related files, sort of compressed versions of these work files that have only a subset of the information inside of them. So the work files are really like the ground truth of everything, and that's what we'll need. If you click this link right here, this workpaths.gz, this does not contain the work files themselves. This contains the URLs to the work files on Amazon S3. So if I click this right here, it'll ask me to open it. You'll notice that the file itself is 200 kilobytes. So 200 kilobytes just of URLs right here. Can I make this bigger? I apologize, it's not zooming in. But yeah, hopefully you can see that these are just, each line here is a different name of a file. All of these files on the Amazon S3 service, there are 64,000 of these files. Each one of these files is about 1.5 gigabytes in size. So that adds up to quite a lot of data here. In order to run this work downloader script, here. In order to run this work downloader script.sh right here, this script, what it's going to do is it's going to spawn a new Docker container that its whole purpose is to download this, whatever URL you pass in as the first parameter to it. And so we have to figure out what is the URL to one of these files right here. The files themselves contain the just the name of this document over here. The document I opened by clicking this contains the name of the file on Amazon S3. In order to get a URL to that file, I have to prepend this to the front of it. So I'll show what that looks like. You'll do something like sh downloader work.sh, then paste the data.commoncrawl.org. This is the, will link us into Amazon S3. And then one of these file names inside of there like that. And got the enter here. So that's what the actual command is going to look something like this. Over here is the URL like that. And again, the URL came in two parts. The first part here had to just paste there. And then the second part is the actual name of the file. This is the, I don't know, key step where a lot of people get confused, just like the mechanics of doing this. Are there any questions about that? Okay, this step right here takes maybe an hour or so to run. It has to download, again, 1.5 gigabytes of data. The Lambda server and Amazon.s3 both have really excellent internet connections, so it downloads at about 50 megabytes per second. So the download time isn't really the bottleneck. It's the insertion into the database that is a bottleneck and takes a long time. And if I run Docker PS right now, I have, so I should have ran this earlier. There's these 3 services that correspond to the standard web services, the PG, web, and PG Bouncer right here. But then this downloader work service also got added, you see here about a minute ago. And you can see right here, here's the file that it's trying to add for us. And as part of this, this assignment, you have to, as this task 2A, we don't want to load just one of these work files. You have to pick 5 of these different work files that correspond to different time periods and load those up into the database. I'm going to go ahead and just load a second one so that we can see what the Docker PS command will look like. So again, starting with that domain right here, URL, and then over here, selecting one of these files and pasting it to the end, and then it'll start that download, Docker PS. Now there's 2 of these containers running. And again, because this download is running inside of a container, if I was doing this on AWS or a cloud provider, I could have arbitrarily many of these running on different machines, using up as many resources as I wanted, as much as I had money to spend for. This assignment, though, only asks you to do that for 5 of these different files. Any questions about that? Really? Question is, can you choose any 5? And the answer is yes. It doesn't matter which 5 as long as they're from different time periods. So the time periods are, each one of these sort of lines corresponds to a different time period. And so if I were to click on like March 2017 here, these are not like web pages that were necessarily created in March 2017, but it's all of the crawls that it did in March 2017. So this will have web pages created in March 2017 and earlier, but not something in, say, like 2018. Good question. Any other questions? Yes.
What was it? Oh, sorry.
Question is, how do you know when the data is done loading? And if you do, so Docker PS like this, these containers will automatically kill themselves when the data is done loading. So one way you'll know is that they will just disappear from the Docker PS. Another way is that if you do, so Docker logs, and then I'll add a -f, the -f standing for follow, so it's not going to end this right away, and then put one of these commands, we can see the output from the loading process as it's going, and eventually it will say that it's done loading things. We see here it's doing inserts, sort of 100 web pages at a time. Again, there's lots of sort of processing that it's doing on each one of these web pages, so it takes a fair amount of resources. So let's see, it took from here, it was 5026 down to 5053, so about 30 seconds to load 100 web pages. Let's see, was somebody on Zoom asking a question?
Yeah, Professor, I just have like this question. When you meant like 5 different links, do you mean like 5 different times? So we need to load all the links inside the file when you open it?
Question is, do you load all of the links, all of these inside of a file? And the answer is you do not. You do not have enough disk space. It would be impossible for you to do that. There's 64,000 of these files. That's roughly, so each file again is about 1.5 gigabytes. So that's roughly 100 terabytes of data that they crawled in March 2017, 100 terabytes of data. So that's a lot of data. You couldn't even load you couldn't even store all these files on the Lambda server. So that's why you're just picking one, definitely not doing the entire data set.
So if I understand correctly, we pick one right here, we choose another date, and we pick another one, and like we choose 5 links for the whole thing. Is that correct?
That is correct.
Thank you.
Oops, okay. And so that is your task 2A over here. We want 2 other ways that you should be checking to see that your processes are working. We talked about the Docker logs already. Let's talk about like ways using SQL over here. So if we do docker compose exec pg psql, again, this is not going to work by itself because I have to specify the user -- user equals Novachenko, like that. And now, so here's all of the tables. There's a lot of stuff inside of this database. This meta HTML table is the one that things are being loaded into. And if you do something like select count star from meta HTML, you should see this count, the number of web pages that have been loaded increasing. So currently, when I ran it before, see it ended in 208, waited a couple seconds, now it's at 608. So this number should be going up. You should also start being able to go to your, as long as that number is bigger than 0, you should be able to go to your web page over here and type something in. Here, when I type in Iraq, it's searching those 500-ish thousand web pages that have been loaded for web pages that contain the word Iraq. So 3 ways that you can check to see that you're actually successfully loading the data and completing that task 2A. One of the downsides of working with these work files directly, loading it directly in, is that you have no selectivity on like what information you're loading. You're loading from just random crawl of the internet, lots of potentially high quality web pages, but mostly low quality web pages. And so the idea of task 2B is to not load work files directly, but instead load files that correspond to a particular domain name that you want to be able to search. And this downloader host service is going to download all of the results for a particular host name. So if you want to load the New York Times or foxnews.com, whatever it is, you'll be able to load that in and search that domain for articles about your favorite topic. In order to do this, there are, let's see, there's three fix me statements that you'll have to fix inside of this downloader host.py file in order to get the code to work. In order to describe what those fix me statements are going to do, we have to talk a little bit more about the common crawl index. So actually, maybe before we talk about the common crawl index, one thing that I've glossed over so far is this top part up here, that this graph. What this graph is showing is the publication date of these articles down here. So there are, in 2003, this particular month, September, 0.05% or 5% of articles mentioned the word Iraq that were published at this time period. In order to get that percentage, we have to be able to figure out when an article was published. And also down here, in order to be able to like show summaries of an article and show this title, we have to be able to somehow extract that information from an article. The particular meta information that we're extracting from our articles are so the publication date, the title, a description of the article, and the text. And this information is stored in HTML through something called the semantic web. And the semantic webs, back in the 90s, early 2000s, it was a super, super popular thing. Everybody was trying to get people on board with the semantic web. Occasionally this sort of pops up again. But I think at this point, people generally feel like it's sort of a losing battle. Nobody who's building websites is going to make them for the semantic web. But the idea of the semantic web is that you could annotate your HTML with a lot of cool information. So some of that cool information being like the publication date of your web page. And the fundamental problem was that basically everybody decided to create their own different system for annotating this information. And so because of that, yeah, there's just too many systems. Nobody follows all of them. And a lot of people end up making up their own systems. So things like BBC and FoxNews.com, both like major web pages, you would think that if they would want to follow like a standard, neither of these web pages follow any standard. They make up their own standards. Another problem is just Americans insisting on putting our months and dates in the opposite order of everybody else in the world. And so in order to know like the actual date of a web page, you have to know whether the person who wrote it is an American or not an American. So lots of problems with the semantic web stuff. But I have a library that tries to deal with those problems. It's in use in the search engine trying to extract this sort of information. So you don't have to deal with any of that. It's just going to extract that automatically. There's two open research tasks related to this that I want to mention. So one is related to the question that Kieran asked before about like, what about web pages that don't want to be crawled? And in particular, I think dynamic web pages are sort of an even broader scope of a problem. So if you have like a login that you need to access a web page, that's never going to get archived. Things like Google search results, they change depending on like who you are, where you're accessing from, all sorts of factors. And so you can't like archive Google search results. We will never know. This information is lost to the universe, like what search results people were getting for coronavirus in January 2020. Some people think that coronavirus was already well known at this point. Some people think it wasn't. We will never know for sure because Google is not archived and in principle not archivable. Other things like Amazon prices, those change all the time. So really can't, are very, very difficult to keep track of. Less obvious things are if you have web pages that use JavaScript incorrectly. And one example of this is the North Korean KCNA webpage, main newspaper of KCNA. They used to use JavaScript incorrectly, and so Google and archive.org couldn't index them. I helped them fix that though, and so now we have archives of North Korean newspapers where we never used to before. The link describes why that's cool if you're interested in that. But this is just sort of like a general problem that the web page actually has to fix itself in order to be able to index that, search it. You can't do anything, or it's exceptionally hard to do things on your end as the scraper, the data processor, to fix the web page. Another open research problem. So I have this meta HTML library that does extract some information from a web page, but it's really like a very ad hoc system. it's an exceptionally hard problem to do in general, again, because that semantic web, there's just so many standards out there. And at this point, not even Google has a good solution to this. The existing solutions sort of somewhat work for English, but basically don't work at all for any other language, especially Asian languages. And it's not, at this point, to me, clear if this is due to a lack of research or just like some languages are harder or people just don't care about this problem. But this is, makes web search significantly more difficult. Makes analyzing web-based data sets significantly more difficult. What we're going to talk about next, that task 2B. Any questions before we get to the task 2B? Okay, so in the task 2B, again, we're giving a particular host name and we want to find all of the web pages related to that host name. And so in order to do that, we need fast access to the just certain locations inside of the Common Crawl or Internet Archive databases. And anytime we have a large data set and we're trying to get just like certain parts of it, the idea is we'll use an index. And because the Common Crawl Internet Archive is so large, these databases do not use Postgres. They use a custom index format. Again, Postgres has storage overhead of about 2 times due to those internal file format issues that we talked about. And for the vast majority of data sets, anything less than, say, 100 terabytes, so anything that probably any of us are going to be working on, that is not a big deal at all. But for something like Internet Archive, where your database is in the petabytes, hundreds of petabytes, or like Google, Facebook, exabytes of data, that really that'll matter. At big scales, at actual things that I would call big data scales, that 2 times factor really adds up, and that'll make your AWS bill way too big. And so that's why people use these custom formats on these exceptionally large data sets. So the idea of this Cdx index, there's 2 links to the using these indexes manually, and we're going to go over for the Common Crawl index how to use it manually. So following this link right here takes us to this web page. And on this web page, so again, these links over here correspond to the to these same links over here. And if we were to say, we'll just do the very top one, click the very top one. Lots of people using this, so it's a little bit slow. But then up here, if I wanted to type, or if I wanted to find information about just a particular website, let's try, so my own blog here, the wiki.me/star. So the star here means it'll find anything that's like inside of my web page or a subfolder. Without the star, it would only return the exact matches to that URL. Let's see, they're all probably HTTPS, so let's do that. Hit enter. Take a little bit to get the results here. And again, that's not because the index is slow. It's just because there's a lot of people who use this, and Amazon does not allocate a whole lot of resources to this. Amazon doesn't care if this returns in 200 milliseconds or less, the same way that Google cares. And so they only have a single computer running this rather than a big distributed, horizontally scaled farm of computers. Open that up, and let's see. I'm gonna make sure that I can actually open up this one in a window where we can all see it, so I can. So type it out, Mozilla user, and then CC. There we go. So each line right here is just a JSON dictionary that contains all the information that's needed to access some particular web page. If I go see how many lines there are, there's 19 lines. So there's 19 different files that they have browsed, recorded from my domain name during that 1 month period. So you can see most of these are boring things like robots.txt, a couple of like actual blog posts in here, and then a lot of just the root homepage like this. Has the timestamp of when it did the actual recording. So the URL in its actual readable form like this. This right here is what's called a SURT form of the URL, S-U-R-T. Anytime you see S-U-R-T when you're looking at the documentation, that means that the URL is in this form right here. The S right here, this is basically means a sortable URL. And in order to make it sortable, they made the domains here go in reverse order. So isbicky.me goes into me, comma, isbicky. And use commas instead of dots just to indicate so that people know that it is a cert and not a URL. And this makes it so that if I had a subdomain, which I happen to, Mike and Kristen.isbicky.me, a subdomain for that I made for our wedding, it'll be alphabetically, and Kristen, like that, alphabetically in order. And so if you were sorting things alphabetically, like a B tree does, then making a B tree index on this key right here would put all of the subdomains of a domain right next to each other. So that's why you'll see things, the domains in this sort of weird order like this. Then it has this file name right here. This file name corresponds to the actual name of the work file that you would download from S3 in order to get access to this particular URL right here, browsed at that particular timestamp. And it also has the let's see, so there's URL key, timestamp, URL, MIME detected, the digest, so a hash of the results. Here we go. The offset, this is the byte number that you would start downloading at this file. You download this file right here, starting at this byte, download this many bytes, and that will give you the work entry for this particular URL right here. So because of this, you don't have to download the entire work file. You can download just the portions of the work file that are relevant to whatever you're looking for. And you can easily get one of these lists of all of the files of what you're looking for, or for any particular domain, all of the locations in the work file that contain web pages from that domain. Are there any questions about this Cdx index or what it's doing? Okay, so because of that, that Cdx index, when we run this downloader host, you pass it a host name as an argument, and you don't need to download the entire common crawl. You can download just the relevant portions and still search those. In order to do that, there's 3 fix me statements inside of this file right here. So let's go ahead and open up this file. This is the important section of code for you to look at. The library, there's an easy to use Python library for doing all of the Cdx information for you, the Cdx Toolkit right here. And so you have to look at this Cdx Toolkit, find out how this cdx.iter function works. Basically returns a work file one at a time, storing it into this result variable right here. And you'll have to look up how to convert this work file into a work record using that Cdx library. Once you do that, given a work record, you'll have to look up how to convert or extract the URL, access that HTML from that particular work record. And then once you have that information, you'll have to extract the appropriate meta information using this meta HTML library. And the way to do this part right here is you should look at the implementation in the downloader work that is already doing this. And basically copy and paste this code in order to extract that information from the information that you got up here. The purpose for doing this is so that you just get familiarity with working with, again, with large code bases, trying to navigate them, finding relevant sections of code, and actually getting your production system up and running. Let's see. One of the things that we're not doing this semester that I would have liked us to do is to basically implement this relevant portions of the Cdx Toolkit library so that you're writing the Python that's actually accessing directly these indexes and processing the JSON. Because of the paternity leave and our compressed schedule at the end here, that's like one of the programming assignments that I've taken out of the course. So you don't have to do that. You can rely on the already created Cdx Toolkit library to do that for you. Any questions on that? Okay, last task, speeding up the web page. So again, we know that there's full text search going on here, the double @ sign somewhere in all that Python code. We don't know where it is, so we don't know what the query looks like, so we don't know how to speed it up. And so how do we speed it up? Well, it turns out that Postgres has this thing inside of it built in called pgstat statements that records all of the queries that get run and all of their runtimes. And so you can look up in this pgstat statements all the runtimes of all your queries. If you do that, leave here, reopen pSQL, just run that query right here. You get, so it's a really big thing because there's some really big queries. And so it'll take you, you have to be a little bit clever about how you navigate that. There is another special command that resets all of these statistics that Postgres is taking. So it might be useful to run pgstat statements reset like that to clear things out. And then after you've reset things, you can come to your web page, just refresh it a bunch of times, make sure that query gets run a bunch of times. And then you can see your slow query will be somewhere at the top of this query right here, see what the query looks like, and then write an index that's going to fix that query. In general, on large programming projects, especially those that involve databases, you're not going to ever understand like everything that's going on there. You're never going to understand all of the like SQL queries that are going into a database. And so generally people try to build their indexes sort of defensively in advance, but you're always going to miss some. And so you need to be able to do things like run these queries, find what is the slow query, and then build your indexes sort of based on this without ever actually seeing the code that's being run. And once you build that index, it'll speed up your full text search. Any questions about that, what to do? Okay, so then submission for this assignment. I want to know what your create index command is. I want to see how much data you've inserted and filling out all these queries. And you just put it's just asking you to edit the README file directly with these results. And then take a screenshot of your fully completed web server, web search engine, doing some sort of search, and submit your GitHub repo to Sakai. see. Seems like everybody's pretty exhausted. I'm pretty exhausted today. So let's end class early today. And if anybody does have questions about this or the homework assignments, I'll be stick around to answer the questions that you have, or I'll be available in office hours today. So yes, goodbye.
Professor,
Huh?
is there by any chance a way I can come earlier than office hours?
Only available during office hours, sorry.
Okay.
Yeah.
Thank you.
Yeah, it's just have other things that I have to do to take care of my kid today, sorry.
Okay, no problem.